Hi everyone, my name is Yang Yu. Let me introduce my research. So my research is fast and efficient AI. I'm a presidential young professor at the National University of Singapore. I got my PhD from UC Berkeley. So in the last few years, we know AI models are becoming more powerful, but they are also more expensive to train, especially computationally expensive, right? So here is the year in the last few years. Here is training cost, right? Even the single floating point operation per dollar is becoming lower, which means the single floating point operation is becoming cheaper, but the total cost is much higher. So we need high performance computing techniques, HPC techniques, to make AI models training, fine-tuning, inference more efficient and cheaper and faster. That's my research. So what's the key problem? We review the product strategy of NVIDIA for the uh, last 5 years. I know NVIDIA has many great strategies, many fancy techniques. But what's the most important product strategy for NVIDIA in the last few years? The key strategy is to put more HBMs in the same space, in the same physical space, from A100, H100, H200, B200. You see, they just put more HBMs. We know HBM is good for large AI models. However, HBM is off-chip. That means we have physical distance. With physical distance, potentially we have a higher latency. That's a very big concern. So how can we make a full use of NVIDIA chip, the growing performance? How can I make a full use of the GPU servers? We need a massive parallelism. The massive parallelism is the only solution we can use to maximize the performance for hundreds of thousands of GPU GPUs. So that means NVIDIA needs very high parallelism from the software level to hide the latency. So we have better hardware, but we need a very high software parallelism, and then we can achieve the best performance. So without parallelism in the software, we cannot maximize the performance of the hardware today. So my research is to design and implement empirical methods to make AI run faster and more efficient. That's high performance computing for AI. So specifically, the focus of my research is to extract more parallelism from AI workloads to mask the hardware latency. So to extract more parallelism, I designed the system level techniques, algorithm level techniques, and optimizer level techniques. So let me use one example to introduce my research, LARS and LAMP. So firstly, let me introduce large-based training. Assuming every iteration you use 2 million tokens to train your model, you need 400, 400 million iterations, right? How about now you increase the number of tokens by 10 times per iteration. You also reduce the number of iterations by 10 times. I mean, with larger batch or more tokens per iteration, potentially you can make a full use of more GPUs, but you can also reduce the number of iterations. Double win, right? It's a win-win solution. However, the concern here is you make the base size very large. Often you converge it to a bad minima, like sharp minima, right? With very poor generalization. We want something like a flat minimum with better generalization or a stable solution, right? With sharp minimum, even you can train faster, but the model quality is very bad. We want to avoid sharp minimum. Even we want model train faster with light-based training, we can use more GPUs, but we cannot accept sharp minimum because the model quality just is terrible. So to solve this problem, I propose the loss and lamb optimizers. So the key idea of loss lamb is trust ratio. So for the image or video model, like we use loss, trust ratio example is the normal weights over the normal gradients for each layer. We compute this dynamically, and then we use this important navigation to help the model to train stably and very efficiently for very large base size. And also we use a similar idea for LAMP. By doing so, the model can train very fast with a very aggressive learning rate, and all the layers can be very stable. Eventually, we converge to a very good minima. So here is the key idea of loss and lamb. With better navigation, we can train faster, and also we converge to flat minima. We want to avoid the sharp minima. We train fast, and also we are stable. That's the key idea of loss and lamb. So here are some of applications of loss. So from the year of 2015 to the year of 2020, people reduced the ImageNet training time from 29 hours to 30 seconds. Right? So since 2017, all of them actually used LARS. LARS were used by Tencent, Sony, Google, Fujitsu, and Google. So a few years ago, Google trained for the first time, Google trained their AI models with 4,000 TPUs. Right? So here is a paper from Google. They also use LARS and LAM for training their AI models. Snapchat use LAM to train their video generation model Snap Video. So here is a paper from Snapchat with LAM. So they can train the model with large batch and more stable and more scalable. Also, the convergence is better. So also from NVIDIA public GitHub, we can see LAM can be 17 times faster than state-of-art solution. Right? So here it's from NVIDIA public GitHub. Also, MobileNet V3 is one of the most downloaded AI models in the June of 2025. So this model was trained by LAM. Also, US DOE Oak Ridge National Lab, they use LAM. They can make the training 60% faster. And Facebook perception encoder, all the core trainings are using LAM. You see, for image pre-training, video fine-tuning, distillation, all of them use LAM. LAM is also implemented in Microsoft's DeepSpeed. So LAM is Shopify CTO's favorite optimizer. And also Benjamin Mann, who is the co-founder of Anthropic and also the co-first author of GPT-3 when he was at OpenAI. Before he trained the GPT-3, he used LAM to scale the transformers to 128 GPUs for the first time. This was very important for the early study. Even for today, you can search on the internet. And Google used our LAM to reduce the bird training time from 3 days to 76 minutes. And after LAM, we also we also designed and implemented some new optimizers. We win the ACL and AAA Distinguished Paper Awards. Even for today, LAM was used by Microsoft DeepSpeed, ByteDance Megascale, 10,000 GPU cluster, and also NVIDIA. So we also trained our own model by our own infrastructure software, by our own optimizers, training techniques, right? That's open source, right? It's open source. Open source got over 26,000 GitHub stars, and we minimize the training cost. We just use 200,000 US dollars. Very efficient. And we put everything together, build the Colossal AI software. Colossal AI has ND parallelism, tensor parallelism, life scale optimizer, and memory management, first inference. Colossal AI is a very good software for training AI models. So Colossal AI has got 46,000 GitHub stars, similar to DeepSpeed and NVIDIA Mac-Tran. So here is AI infrastructure overview. So firstly, we have the hardware and the low-level software, cluster management, inference software. So Colossal AI is here, and then AI frameworks, and then the AI models. Right? So my research is in this level. We build the HPC techniques to make AI models run faster and more efficient, it's high performance computing for AI. And so here are some of my research awards. I was nominated by UC Berkeley for ACM Dissertation Award. Only 2 students were nominated by Berkeley. And I won the Presidential Young Professor Award at NUS. It's a highly competitive tenure track position for early career faculty. And I also won the IEEE CS Early Career Award for HPC. And I won the ACM George Michael HPC Fellowship. This was the only PhD fellowship on SM homepage in 2017. And I also got the award for research when I graduated from UC Berkeley. I also won some paper awards. Firstly, I was a corresponding author. My student is the first author, AAA, ACL, ICRR, CVPR. Myself is the first author, ICDM, ICPP, and IPTPS. Thank you.